Welcome to this first segment of acoustics. We have discussed in the introduction the major content of this course, which will be primarily on the sound waves which propagate in fluid media. We are not going to discuss anything focusing on structural acoustics, that is sound waves that propagates inside structure. So having said that, in fact this first segment or the first unit in fact will not be directly in any way related to acoustics as such. We will be building some vocabulary, some mathematical foundation on which we will be discussing our subject acoustics. Now this first unit is in a way common to vibration and acoustics. So it's like that, because anyway as you can intuitively also think that acoustic waves primarily are generated from something vibrating somewhere. So vibration and acoustics are so closely related that the vocabulary which is used to describe vibrational phenomena are very commonly used to describe acoustic phenomena as well. So from that perspective we will be discussing some foundational concepts which will be very helpful in understanding the acoustic concepts once we get into deeper acoustics. So to start that, what I'll in fact okay. See, when we say a sound wave is moving, in fact suppose in air, okay, then what actually is happening physically, all of you have studied in your 12th standard, from 12th standard onward, that it's a longitudinal wave and the air molecules, or I will come to that whether we should call molecule or particle, all those things. So air particles in fact oscillate about their mean position, and that oscillatory phenomena propagates, and that you perceive as sound. Okay. Now I intentionally use the word perceive because we will also be talking about what you actually physically hear and what you perceive. They are two different things. In fact, a lot of things needs to be discussed about that. Okay, perception plus physical means phenomena. That means a robot, what a robot will hear and what a human being will hear, or what a particular animal will hear for the same physical sound which is existing. So all those things we will be discussing, but then whatever it may be, the major thing is that something vibrates, something oscillates, and when something oscillates there are two parameters which come into picture, and or I should say we should concentrate on, and they are at what rapidness things are happening, okay, and so that tells us about the frequency, okay. So with what speed things are changing. So one part which is the primary thing, is frequency, and the other thing which is important is the time, okay. Though you may be thinking now that okay, how rapidly something is changing is related to both frequency and time, and then they are definitely related to each other, but what I am trying to mean is that there are two ways to investigate or analyze the systems where things are vibrating, oscillating, or the sound propagating, okay. And those two ways are like this, means whether you can think in terms of frequency with which things are vibrating, or you can think in terms of time, okay. So we will be discussing a lot about them, so just be patient. everything may not be very clear now, but anytime, anywhere you start thinking about any phenomena of vibration or acoustic, first question you should ask yourself is, am I thinking in terms of time or am I thinking in terms of frequency? Okay, now we will just discuss now what exactly do I mean when I say thinking in terms of time and thinking in terms of frequency. And now, but okay, let me in fact start the discussion itself, and we will create this vocabulary of frequency and time domain analysis. Okay, so say frequency domain, you will always hear this vocabulary, and time domain. Okay, analysis. Now, what exactly do they mean? Let's discuss with the simplest of the examples, and in fact what I'll do, I'll draw a series of cases with increasing complexities. Okay, and in fact the acoustics, the whole course also we will be studying in those incremental steps. Let me first tell them and then I'll elaborate. Now the first thing, the first case, if I may say so, is something like this. Suppose there is a spring and there is a mass. Okay, so this is the simplest thing which you can think of which oscillates, right? A spring and a mass. I haven't put even a damper there. Okay. Now, first of all, why am I even talking about springs and masses and dampers when we are talking about acoustics as a general in this course? See, the thing is, any dynamic system in the universe can be thought of to some approximation as a combination of many springs, masses and dampers. So that's the basic theme on which in fact we will build up this course of acoustics. Okay, so these three things are very important: springs, masses and dampers. That means or in fact let me put that in the previous slide. We will be talking in terms of everything in terms of springs, dampers and say masses. Now when I say spring, it means some stiffness. Okay, some stiffness of the system, whatever system it could be. It need not be a physical spring, a physical object. It could be a financial system, it could be in fact an emotional system, it could be the behavior of a society. Anything which changes with time will have something which can act like a stiffness. What is stiffness? That means if you try to change it, it will try to come back to its original condition. Okay, it doesn't like to stay in its changed position. Okay, so that's what is the stiffness or springiness, if I can say so. Okay, like a spring, you push it, it tries to come back to its original length. You pull it, it tries to come back to its original length. So that's the stiffness part. And damper, so this is in a way means, what do I call, in which things die in a particular rate. Okay, so they die, everything dies, okay, at a particular rate. So means when I say dies, suppose you created a vibration, it dies out after some time, right? So that's what I mean, means it decays, okay, or a better word could be, yeah, so decays. So that means everything has a tendency to die out, decay. Okay? And then that property of a system, of any dynamic system, is termed as damper, okay, in general. And then this is the mass. It need not be a physical mass. Suppose in a financial system, what could be a mass? But there will be something which will behave as a mass, or we will call that as, you know, inertia. That means the general things are stiffness, the decaying property or the inertial property. Okay, that means, what is inertia, by the way? Means you tell it to do something, it will do, but it will not do it immediately. It will take some time before it responds. So that's what is inertia. Okay, so for any system. So these are the three prime factors, in fact, which can be thought of, that any complex system can be broken into these smaller pieces. There could be many masses, many springs and many dampers, or many levels of inertia, stiffnesses and damping, but you know what I mean, right? So it can be a combination of such things, but we are here, I am just drawing the simplest of such thing, only one mass and one spring, not even a damper. Okay. Then yeah, I was trying to put things in order of complexity. Yeah, so then the first thing is, I am not even applying any force to it, but it can oscillate. How it can oscillate? You can pull it and leave it. Okay. Now, so generally students have a feeling that particular thing which I described now is like applying a force, but I am saying that no force. Okay, I am talking about no force. So that no force condition in which the things will vibrate. Okay, or in fact, there are two parts here, right? One is you pull or push, or you just hit with a ball. Hit with a ball or something. Okay, tuck, and then it starts oscillating. Now these are not, in a way, we won't call them as forces. They we will call them as some initial conditions. Okay, that means you pulled it, that means you gave a displacement initial condition, you hit it, so you instantaneously gave a velocity. Okay, so that means it's delta initial condition and it's a velocity initial conditions. So you are just starting the system with an initial condition but with no force. So this thing, the vibration which happens here, is called as the natural vibration. Okay. So any system which has these springs and masses, just from an initial condition they can set into vibration which will just be continuing, because here we don't have any damper, so it will just keep on moving like that. And then, so that's the natural. So these words are very important, because these will keep on occurring again and again in different contexts, but you should again completely be clear about these things, that there are no forces, only initial conditions. Okay, that means initial conditions, see, in this case you are giving a kinetic energy to the system somehow, and in this case you are imparting a potential energy to the system. In fact, you can give both of them together. That also is a possibility, that you pull it and still you hit it. Okay, under that condition it will be a combination. You gave both a potential energy and a kinetic energy, like that. So that's the first case. So any system, if you want to study its vibrational or acoustical property, this should be the starting point to think about. Okay, what is its natural vibration characteristics. Then what? The second one is the same thing. I'll not change the system as such. I will keep it like that, but then I will apply a force here, okay, which is changing harmonically. Okay, so yeah, so harmonic, I'll call this harmonic, or yeah, so that's the word which is generally used, harmonic. That means these are completely sine or cosines or the shifted versions of them. Okay, this force which I am now applying is on this body. I am applying the force, and that force is varying. Means suppose this is a 5 Newton of force, and whatever the time period is, okay, with respect to that, if I write this F, so this F will be, say, the amplitude times, say, sine of 2 pi f t, right. So this F is nothing but 1 over this t, the time period. So this kind of a force, when you apply on this, so it's you are giving a harmonic, analysis, you can say. So this is natural vibration analysis, this is harmonic analysis, and this is completely different from this one. Okay, here you are studying the complete inherent property of the system. No external thing is happening. Okay, you just gave some initial conditions which could be anything, and then you left it, and the system is on its own. So you are basically studying its inherent behaviors, inherent characteristics. Here you are actually applying a sinusoidal force, okay, or displacement or whatever. In this case, suppose force, be simple now. Force you are applying, and then you are trying to see how the system is behaving. Will it so now I am applying a 5 Newton of force with a particular omega or frequency, say 10 hertz. Then how much will it vibrate? What will be its amplitude? Okay, will it also oscillate at the same frequency of 10 hertz or something else? So these are the sort of things which are under the discussion of harmonic analysis, and basically it is generally done at various frequencies, so that frequency, you say at 10 hertz, once you do the analysis at say 10 hertz, once you do at 20 hertz, 30 hertz, 40, so like that at every frequency you carry out this analysis and then try to see what's happening to the amplitude of vibration or some such things, and then talk about that. So that's called the harmonic analysis, and so that's the next level of complexity. And then I would go to, suppose, the third one. Sorry, I'll put the. Now the third one is the same. I'll not change the system. I'll just change the force a bit now. So this force was anyway acting like that. I'll change the type of the force to something say like this. I'll say something like that. Okay. I have tried to draw a very similar curve here. It doesn't look very similar, but try to see that. Okay, I wanted to make something like this. In fact, after this also, so like that. And what I meant was up to up to this point and this point. So they are the same segments. Okay, but they are not now harmonics or sinusoids. So it's just a periodic. Okay, periodic. So this being the period T. Okay, in the previous case, in this, the period was the period of a sinusoid, a sine or a cosine, like that. Okay, but here it's a random shape, but which is repeating. Okay, so that means it's a periodic one, but not harmonic. All harmonics are periodic, but not all periodics are harmonic. Now, if I apply such a force, then what happens? How to analyze that? So that's the next level of analysis which we generally perform. Okay, and then what do shall I draw it in this? The same, yeah. I'll do what I'll do is I'll move this part here. Okay, so this is periodic. Now what I'll do, the fourth case, in the same system, just the force has been changed now to a completely arbitrary shape which in all these cases, I wanted to draw this is in time. Okay, the x-axis is time. I should have mentioned here also. Okay, the x-axis is time. Here anyway there are no forces, so it doesn't matter. Here everywhere I wanted to draw on time axis. Okay, so this force is changing with respect to time now arbitrarily. So that is completely aperiodic signal. Okay, I'll call it aperiodic. Okay, completely it will never come back. The shape, if you take any length of shape, that shape will never be repeated again after how much time, forever time you wait for that. Okay, so that's the 4 level of increasing complexity. You see that? No force, natural vibration, sinusoidal force, harmonic vibration, a periodic vibration, sorry, the periodic which is not harmonic, then aperiodic vibration. And this we are dealing with the simplest of the system. Okay, now once we go to acoustics, this system will change, but this approach will remain the same. So that's why I am emphasizing on these concepts, so that you should be very clear about what we are talking about when we are using a particular terminology. Okay, so yeah, so that's the thing. And then suppose I go to another, I'll increase the complexity. That was the 4th point. So now the 5th point, I'll just maybe I'll add I'll change the system now a bit. Okay, so this was the system. Now I have put a damper here. Okay, now this one with again no force, so it's a natural vibration. Then again the 6th one will be its the harmonic, then the seventh one it's periodic, and the eighth one it's aperiodic. Okay, of the spring mass damper system, of the spring mass damper system. Yeah, so like that. So these are in a way the eighth or 8 level of complexities which I increased in a way, and then yeah, so we will in a way we will increase the complexity from here to include more masses and more dampers. Then we will go to continuous systems, because as you increase the number of masses and the number of springs and dampers to a very large number, you can then approximate that to be a continuous system. And those things like a string, the string of a say a piano or a guitar, right, when it oscillates, when it vibrates to generate the sound. So that will be a continuous system, not a discrete system like this, a single mass or a single damper. Let me, okay, I've drawn it here, so why don't I draw even that? So suppose there is another level of complexity when I increase, say this is a spring, sorry, this is a mass. I attach, sorry, what I'll do, I'll attach a spring, a damper, a mass, a spring, a damper, so like that. Okay, so suppose this is the case, and then consider, assume the flow to be frictionless or otherwise, doesn't matter. So this is a case where it's a 2 mass system. Still it's a degree of it's a discrete system, it's not a continuous system. But when these mass and springs are means huge in number, almost like infinite, you can get into the concept again. In this case, again, all those 4 cases of natural, harmonic, then periodic, then aperiodic. Okay, so these 4 cases, under such conditions you can always talk about. Okay, that means suppose you are applying a force here, F1, a force here, F2, and these forces could be 0, harmonic, periodic, aperiodic, anything. Okay, so under such conditions, again some discussions can happen. Then you go to say, I'll call this case 10, where you have a completely a system, continuous system like that, and then it starts oscillating. And again, all these 4 cases you can discuss for that system, and then you can talk about the simplest of the acoustic system. It's a tube sort of thing, and you have, say, molecules of air maybe. Okay, and now what you do, okay, what you have done is you have put a piston, something like that here, and keep oscillating this piston, so like that. Okay, then what happens is these waves will start propagating, and again the same thing. Here you will have some sort of mass, some sort of damping, and some sort of stiffness. Okay, in this air also you might have felt, isn't it, Suppose you have blown up a balloon or something, and then you try to compress it, you can feel the what do you call, the stiffness. In fact, that stiffness is also from the stiffness of the rubbery material of the balloon. Another example could be, if you foot pump, you close the other end of the foot pump, the tube that comes out of the pump, which you use generally to pressurize the tube of your bicycle. You hold tightly the other end of the tube, the open end of the tube, and then you apply the foot pump. What you can see is it will go there, and if you release the foot, it will come back. So that tells you that air has got stiffness. Similarly, air also has a very nice damping property, and air also, that it has got a mass, though it's very small, but still it has got a mass. So these three things, they will interplay and they will make this disturbance propagate. And so that's how we will, again, these oscillations which you do here now could be natural. We will come to that, what exactly do we mean by natural here. Okay, and then it's harmonic, and then periodic and aperiodic. So this is how we will proceed in our discussion in a way. Okay. So and not in complete details for that matter, we will spend some time here in this case. Okay, we'll spend some time on this so that our concepts will become very, very crystallized, and then once we are quite comfortable with that, we will slightly discuss something about this, not much, but we'll spend some time, because concepts like modes and mode shape, modes, then what do you call, natural frequencies. Natural frequencies. So all those here also there is natural frequency, concept of natural frequencies, but here you will have multiple natural frequencies with which a system can vibrate. And here once we come, we will see that how that multiple becomes infinite. So it will have infinite number of natural frequencies, and then we will be completely ready to jump into the actual acoustics here. Okay, so that's how we basically are planning to move into acoustic by increasing the complexity step by step. Okay. Yep, I think that should be fine for the first segment as an introduction to show how we will build up the vocabulary. See you in the next segment.